Hi everyone. So today's lesson hopefully is a little bit easier than yesterday's concept. So this is going to be section 8.05, divisibility. So I'm sure you all have obviously a concept of divisibility, where numbers divide other numbers. But let's actually put just a general definition to divisibility. So first, let's suppose that d is an integer and a is an integer. The idea that d divides a is to say that, or essentially another way to put it is d is a divisor of a. Some other ways that this may be written: a is divisible by d, and a is a multiple of d. So essentially, the idea of divisibility, we have two values, and any of these four ways describes what's going on. So d divides a, d is a divisor of a is divisible by d, and a is a multiple of d. So our formal definition here, using our notation, is that there exists a j that's an integer, such that a equals dj. So let's take a few statements here where we're going to determine, are these statements true or false. So first, let's assume that both d and a are not equal to 0. So the notation that we use for divisibility is essentially a bar. So we would say 3 divides 12. That is true. So in this case here, we would have d divides a. That's essentially our notation here. So in this case, 3 is d and a is 12. So 3 divides a. That is a true statement here. 12 divides 3. Well, that's a false statement. We know that if we did 12 divided by 3, we would get this statement here. But essentially here that's saying 12 divides 3, which we know that it doesn't. If we did 3 over 12, we would not get an integer, which is what we have claimed that we would have. So here, looking at this, let's get some other notation. So if we have 0 divides a, this is false, because then we would have a divided by 0, and we've assumed that d is not equal to 0, so this would be false. D divides a, well, that's what we're assuming here, so we can say, oh, not a, excuse me. D divides 0, that is true, because we have, well, let me go back here. So the previous one here, the issue is not that we assumed d and a to not be 0. We essentially assumed that here d and a could be 0, but specifically D in this place, if it was 0, then we would get undefined. And we know that that's not good. We don't want undefined. But if I had 0 over D, that's fine. That's just equal to 0, which I know is an integer. So it's not a big deal. So this one is true. If we have 1 divides A, that is true. And A divides A, that is also a true statement. So the big issues here is when we have a value that's going to give us a decimal and then a value that is undefined. Because essentially, if we go back to our definition here, if I solved for J, it's basically saying that A over D equals J, where J is an integer. So I have to have a whole number here. It can't be a decimal. So that's essentially what this is saying here, our definition. But this is the formal definition that we'll use when we are doing proofs. So let's jump into our first proof, because I think that seeing the proof will kind of let you know that this is not as a hard concept as it may look with our definitions. So our first example here is sorry, I'm looking at my notes here. If D divides A and D divides B, then A plus B, no, then D divides A plus B, the quantity A plus B. So first, to prove this, we're going to prove this directly. So since this is just an if-then statement, I assume the if part. So assume D divides A and D divides B. By definition of divisor, let's count how many times I'm going to spell this word wrong. By definition of divisor, there exists a J in Z such that A equals DJ. And there exists a K in Z such that B equals DJ. Or excuse me, DK. Okay, so let's look at the following here. So when we do this, as with any proof, we've assumed the if part, we've hit it with the definition, and now we need to work our way to the then part. So we want to actually start with the then part. So let's go ahead and start with A plus B. And our definition of divisor here is we want to get it to be such that we have this quantity, A plus B, being equal to D times some integer, whatever that integer value may be. Let's just say that it's M. So we want to get to that point, because once I've said, hey, I started with A plus B, and I've said it's equal to dm, well, then I can hit that with the definition of divisor, and then we're good to go. So let's go ahead and get started. So we have A plus B was equal to dj plus dk. So sub A equals dj, B equals dk. We're going to factor out a d, so we get j plus k. And this is a lot shorter than we anticipated. So we can actually just sub in m equals j plus k. And we can say, since j plus k has neither fractions nor decimals, there exists an M in Z such that A plus B equals, not 2M, oh, no, not proving that this is even, equals dm. Therefore, by definition of divisor, D divides the quantity A plus B. And we're done. So as you can see, these proofs can be pretty simple. They're pretty similar to the proofs that we've done before with even and odd. But now we are using a different definition. So we're no longer using even and odd, we're using divisibility. So let's look at another proof that's a little bit more complicated. So here we want to prove that if a C doesn't divide the quantity AD plus BC, then either A doesn't divide B or C doesn't divide D. So looking at this proof, just thinking through, I see that I have some negations going on, and I have an essential expression here. So that makes me think that I need to use the contrapositive, and that's exactly what I'm going to do. So our first statement here, so we will prove the contrapositive, which is the statement. And again, the contrapositive, we negate and flip the if-then. So we get if both, so when I negate an either or, it turns into both and. So if both A divides B and C divides D, then AC divides AD plus BC. So that's our contrapositive, so we can say proof of contrapositive. So again, we start with the if part, so assume both A divides B and C divides D. We're going to hit it with the definition of divisor. So sorry, I think I need to charge my stylus. It's getting all wonky on me. By definition of divisor, there exists a J. We're going to put these together, a J and a K in Z, such that I'm going to make this mistake, and I caution you to not make the same mistake. I was just about to write A equals BJ, but I need to be careful here because my statement is that A divides B. So in terms of thinking what is the greater value, B is the greater value. So I essentially need to have B is equal to some multiplied quantity. So I need to be careful here. The statement would read B is equal to AJ and D is equal to CK. So now I need to use my definition or my then part and try to work my way into some sort of statement. So let's start with our then parts, the quantity. So we need AD plus BC And we need to equal that something such that we have AC times some integer. So we want to work our way into here. So I know what B and D are equivalent to. So I'm going to go ahead and sub those in. So I get A times CK plus AJ times C. So I need to justify what I'm doing over here. So sub D equals CK, B equals AJ. And then we can go ahead and simplify here. So we get ACK plus ACJ. Distribute. And now I'm going to factor out an AC, so I'm left with K plus J. And we've finished this proof sooner than we imagined, so we can put this up here. So we're going to say we factored. Sorry guys, I need to charge my stylus. It's getting all funny here. But bear with me, we're almost done. So factor AC, and then sub M equals K plus J. And then we can finalize by saying, since K plus J has neither fractions nor decimals, there exists an M that's an integer, such that AD plus BC equals ACM. By definition of divisor, AC divides AD plus BC. So open box here because this is just the proof of the contrapositive. So we just need a final statement saying, having proven the contrapositive, we may conclude the original statement. So I'm going to move this on my next page. Just the final conclusion. So having proven the contrapositive, we may conclude that if AC doesn't divide the quantity AD plus BC, then either A doesn't divide B or C doesn't divide D. And we're done. So the biggest things here is, again, just following that same proof structure. So I knew to use the contrapositive because we had some there does not exist items, and we also had, well, not it does not exist. It doesn't divide something, and we had an expression in our if parts. So we negated the if and the then, and we flipped them, and then showed the contrapositive. So pretty much a pretty direct proof here. This one was literally a direct proof. So I feel like divisibility is a little bit easier than what we were doing before. The only thing that I would caution you on is that mistake that I pointed out before, where if D divides A equals DJ, not D equals AJ. So I know that that can be tempting to do because D is the first value here. D divides A, so you would want to write it the same way that it's written above, but you need to flip the order essentially for your equation. So be careful with your definition, and we will not meet formally on Zoom today. We will meet on Thursday at 1 o'clock. So I'll see you all there. Have a great rest of your day.